Neural networks have very strong representational power. You can show that a neural network with a single layer, you can represent any bounded continuous function to an arbitrary degree of accuracy. So it's known as the universal approximation theorem. And a slightly simpler result is if you've got any Boolean function, any function of true and false, any logical function, and you have a neural network with one hidden layer, then you can represent this problem exactly in every case. And the neat thing is the solution is actually really, really simple, right? So what I'm going to claim is if I have a logical function of two variables, x1 and x2, so each one of them can be true or false, and I'm going to represent true as +1 and false as -1 for convenience. And if I use a network that looks like that, right, the red edges are the weights of -1, the green edges are the weights of +1, and the black edges would be set differently depending on what problem you're trying to solve with two Boolean variables. So if I have a network like that, I can solve any function of two Boolean variables. And that seems like a strong and exciting statement until you realize something. So look at what these hidden units are doing. Right? So the first hidden unit, it has the weights of -1 and -1 for the two inputs. So if you assume that the bias is 0, basically what the first unit wants to do is it wants x1 to be off and x2 to be off. Right? And the second unit wants x1 to be off and x2 to be on. Right? And in fact, what they're doing is the hidden units, they encode all possible combinations of the inputs, zeros and ones. So it doesn't look like a lot, but I only have two variables. I could do the same thing with 3 variables or with 10 variables or with 1,000 variables. And the same architecture would still work. The problem is if I have 1,000 variables, I would need 2 to the 1,000 units in the hidden layer. So that's where the theorem breaks down. So all of these conditions hold if you have an exponential number of hidden units in the layer.